slow way. Well, if we look at what has happened since industrial evolution, actually, so if we look to the period of 1850, 1900 onwards, then we see that we have changes of about, I think here we look from 1850 to here 0.5 degrees. We have had more variation over the time. That's what's clear on the previous slide. But the issue today is that the speed at which we see temperatures changing, that's something we haven't seen over those thousands of years. And we also see, based on all the climate models that are available, if we run a model and we only take into account those natural systems that are ongoing in our Earth climate system, so then we're talking about changes in solar activity, changes in tectonics, volcanic eruptions, and those kind of components, then this green line and the area to kind of show you the uncertainty is where we would be at in 2020. If in those models they take into account not only the natural aspect, but they also take into account the human aspect and the greenhouse gas emissions we produce, as well as others, of course, then this brown trajectory, including its uncertainty, is what the models show, and then we see that the alignment with the observations, it's quite hard to say that human impact would not be there. So we clearly see the impact of human interaction on Earth, on those climate change and global temperature changes. And it's also something that within the IPCC you sort of changing throughout the years. So they will always make statements and add a confidence level to it and state that impact A is likely caused by this or has a very high chance, so they include that. And you see that in 2014 they used words as in extremely likely to make the link with the anthropogenic forcing, so they added a 95 to 100% probability, which is already stating it quite obviously, but still not pinpointing it fully. Well, in the latest report, they state that it's unequivocal that human influence has worked the atmosphere. So that's also a change that we've seen over the years in the certainty that human activity is causing this. We've had the past, you've seen in this slide that we have climate models to kind of simulate how our climate system, I would say, can behave or could behave. Here we see it till 2020, but of course we want to know towards the future what might happen. It's still a computational model, of course. And to get an idea of those future projections, we have different climate change scenarios that can be used in those models to look how future would look like if certain steps are taken or are not taken. There have been different sets of scenarios throughout the year. So in the 1990s we had the Special Report on Emissions scenario, so the SRES scenarios. There were 4 possible future trajectories, and it gives information, so they take into account information on how population might change, what could use or what could happen with economic growth, how they expect in those different possible futures how greenhouse gas emissions might evolve. It's kind of a broad description of what might happen if we go in certain directions. Those scenarios were quite soon outdated. And we got an evolution towards the RCP scenarios, which are representative concentration pathways. They were included in the assessment of, I think it's 2013, 2014. They were actually aimed to be included together with the SSPS scenarios, but the latter were not finalized by the time that a report got published. So they only included the RCP scenarios. If you look at the RCP scenarios, we get different levels of greenhouse gases and how those might evolve, and the radiative forcing that comes forward or that might move forward. We have four scenarios in this case, and they actually cover the range of radiative forcing that can be expected by 2000 UNDER. So you have one of 2.6 watts per square meter, but ranging to 8.5 watts per square meter. 2.6 is the most optimistic scenario. 8.5, as you can imagine, is the worst case scenario. That's looking at the scenarios from an emission point of view, and then seeing what it or how it reflects upon temperatures and so on. What they wanted to do with the SSPS scenarios, those are called the shared socioeconomic pathways. There they did not want to look at how greenhouse gases would evolve, but they wanted to start from a narrative approach, taking into account different scenarios for how socioeconomic factors could evolve, and then see what the impact is on the evolution of greenhouse gases, what the impact is on temperatures, precipitation, and all those different aspects. So in the SSPS scenarios, they kind of define trajectories of how population will evolve, how economic growth might evolve. They also take into account policy that is already ongoing, what you could expect could upcome in the coming years. And so they try to cover in their 5 scenarios a range of if there would be no climate policy at all, or if we have what is in place in 2020 and we don't change anything anymore and see what kind of happens, versus if you have very high levels of climate mitigation in place. If they define those scenarios, it's of course not one scenario for the globe, so it's differentiated per region, country, depending a bit on the level, but they differentiate across the globe how population might evolve in one country or in one region compared to another one. Just for your information, I've listed the 5 SSP scenarios that are now included in the latest IPCC report. Scenario 1, so the sustainability one, and scenario 5, the fossil fueled development one, are rather optimistic scenarios, but still they differ in how they tackle it. So you see that in the SSP1 there are no challenges to mitigation and adaptations, while in SSP5 there are higher challenges to mitigation and no challenges to adaptation. So how they tackle, how technological evolution tackles climate change differs across those scenarios. SSP3 and 4 are the rather pessimistic ones, where inequality is a thing which leads to very high population growth projections in regions such as sub-Saharan Africa, where you also see an impact on how they think the education might evolve in countries. And then the last one, the SSP2, is a middle of the road scenario, which comes a bit down to historical patterns that they continue to the future. That are three types of scenarios that we have seen. These are kind of the drivers of those global climate models. Another way to look at climate change is once you have those models, you could look at how does the world look like in a 1.5 degree global warming level. If you look at the global warming level of 1.5 degree, that means that the mean annual temperature has increased with 1.5 degrees across the world. Of course, and unfortunately, that does not mean that everywhere it gets warmer by 1.5 degrees Celsius. That highly differs across the globe. It gives us an idea of impact and also towards policy directives to look at what would happen with human health in a 1.5 degree warming world compared to a 4 degree warming world, as well as what would happen with species across the world, what risks would come forward. And you actually see that since a year of, I think 2-3 years ago, the approach of looking at climate change from that global warming perspective has increased a lot of impact is used way more than it was 10 years ago. We didn't talk about global warming levels or not to look at impact based on global warming levels. Now it's a quite popular, I would dare to say, way to look at it, because it's also a very it's easier to say if we exceed that 1.5 degree warming level, then we face this and this risk, and it will come with these hazards, and this is what could happen. Then compared to, oh yeah, we have RCP scenario 8.5, it's less tangible to kind of relate what might happen. So in this case, if you look at these, then you could say, okay, based on the scenarios, we expect a 1.5 degree increase by 2030 or 2035 would look like this, and these would be the impacts. And that's also, if you look at the latest IPCC report, and most of the impact graphs come out of that report, is what they show. So you see in the first one, if you look at annual mean temperature, they looked at the observed change per 1 degree of global warming. So overall you have 1 degree, but then you see across the globe that in certain areas it's less than 1 degree, and in others, and the polar regions are for example, a region that come forward, it's higher. You also see that in certain regions they do not have a significant signal, so then that's why you see a blue spot over here. They have it in observed, and then they also see if they simulate what then the change is that you get. So that's a bit also to make the comparison between observations and model simulations. If you look at how our annual mean temperatures would look like in different warming worlds, then we see the impact from moving from a 1.5 degree warming world to a 4 degree Celsius global warming world on the right. Whereas quite obviously that if we would move to a 4 degree warming world, then we have regions in the world, and then the polar regions are one where we have increases of temperatures on annual level to 6-7 degrees higher, which is huge. And we also see that it's quite unequal, divided in where we see the highest impacts. If you would put global plots next to this, where you would see highest concentrations of greenhouse gas emissions and then industrial evolution, then you would also see that that does not map with where we see highest it's not where emissions are created that we see impact, it's the global impact, of course. We can also get information about how the annual precipitation might change, which you see here on the upper right. So we have regions where it gets wetter, so the darker green, green bluish. On the graph, we have regions where it gets drier. For example, if you look at Mediterranean area in Europe, Portugal, Spain, it will get drier in the future, and it's actually quite actual, or a topic in the news today is what's happening in Spain with the high amount of rain and what's going on there. So we have a system that kind of is kept above Spain, warmer air temperatures. We can contain more water, so we get heavier rainfalls. So it's not necessarily because we see there a drying effect on the long term that we can't have effects as we have seen today in that region. So again, we see an overall annual mean reduction, but that does not say anything about the fact what happens with the events. You could have half of your rainfall expected, but if it falls in 4 or 5 days to make it very worst case, then you have an issue. While in other cases it might increase, but it might be more spread and you might have less extreme events. So that's a bit also partly unpredictable how those things might happen and what the final impact of for a region might be. Information about soil moisture. So we have a full range of variables, indicators that are kind of projected towards the future. We can also look at how heat waves might change towards the future. The first graph is work that we elaborated here in our research group, where we looked at heat waves for the present day in Belgium. Those are the ones that you see in blue. So on the x-axis you see the duration of a heat wave, so the number of days that it continues. On the y-axis you see the maximum daily mean temperature. So if you kind of take the middle of each circle, then you can see the duration of the heat wave as well as the maximum daily mean temperature. The size of each circle is a reflection of the intensity of the heat wave, which has to do with the number of hours that you exceed a certain threshold. Those in orange are those that are projected for Belgium under a worst case scenario for the end of this century. And there you see that by the end of the century, in an extreme situation, we might end up with heat waves with lengths of about a month, which is something that we do not at all see today, even not as an outlier. It's something we do not know today. Similar analysis by colleagues in France for Paris, and there you see in see how it's colored. So this darker yellow is reflecting present day. Well, it's actually more end of the past century. They have included the heat wave of 2003 as a reference, and then again you see a projection for the future. Again, worst case scenario, but they are looking at the time horizon of 2040 to 2070. And also here you see heat waves with lengths over a month in extreme situation, and also quite some heat waves that we are not familiar with today. Doesn't really make you happy if you see those impacts. And that's then the heat wave impact. This is not at all yet related with how it might affect human health, how it might affect species, and so on. So That's just stating the impact of changing temperatures in the earth. If we look further into how will climate change impact the world, then the IPCC also looks at risk of species losses. Again, for the different warming worlds, and how many, in this case, it's a percentage of animal species and seagrasses that are exposed to potentially dangerous temperature conditions. So while you see in a 1.5 degree warming world, I think we will be somewhere around, in certain regions, 10 to 20%. In smaller regions, you will see higher values. If we go to a 4 degree warming world, then in certain regions, as all of the species are exposed. Risks for human health, and that's also a illustration of how unequal impacts are expected to happen. So we see in certain regions across the equator, we see some higher risks on human health. It's of course also taken into account how people can adapt to extreme temperatures, whether they're extremely cold or extremely warm. So those are also things that are taken into account in those impact assessments. Climate change will have an impact on food production, of course, and also there we get insights. Some of the impacts, so they also looked at how will they have positive impact. So will in certain conditions, climate change might have a positive impact. To give you one example, if we look at in colder regions temperatures in winter periods, then we expect that it gets warmer in winter. That might have a positive impact, or that will have a positive impact on cold-related mortality in winter. In regions as Belgium and Northern Europe, cold-related mortality is still leading to way higher numbers of higher mortality numbers compared to heat-related mortality, for example. So that's also how it might positively affect certain impacts, but of course overall we see rather more negative impacts than positive ones. They've grouped them in certain categories, so we could also look at cities and settlements and what's happening with flooding, for example. Another interesting graph is to see how future generations will experience our climate. So compared to someone born in 1950 and what global warming that person might encounter versus someone born in 2020 and how that might relate. An interesting graph, and let's see if I can click the link. This is my climate future. Let's see which screen this shows up. Something you could do if you would be interested, but it actually looks at, or it actually tells you, based on the year you are born in and where you live, how much more events you will encounter during your life with climate change compared to if climate change will not be happening. So I show, for example, what it looks like for me. So I'm a 30-year-old, I'm born in Europe, and in a 1.5 degree warming world, I will encounter 1.5 times more wildfires in my life compared to if global climate change will not be happening. If we go to a 3.5 degree warming world, that would be 1.7 times more wildfires than I will encounter in my life compared to if global warming will be happening. If we look at the heat wave numbers, those are often the most depressing and the most severe changes. So in a 1.5 degree warming world, I would encounter about 10 times more heat waves compared to if climate change would not be happening. In a 3.5 degree world, that goes even up to 70 times. That's only being born in Europe. If you look at other regions in the world, depending on when you're born, if you're born in 2020, for example, then the heat waves might increase to an order of 30 to 40 times more than if climate change will not be happening. So if you would want to see how that would look like in your situation, it's an interesting website to kind of see what impacts you can expect. That about climate change. I don't know if there are so far questions or reflections or thoughts. No? Okay. Then something more about urban climates, where we have the interesting interaction in how our built environment needs to adapt to climate change, but at the same time is a very high contributor